Today we'll be studying the organic chapter, that is organic chemistry's first chapter of class 12, haloalkanes and haloarenes. So here the first term we have haloalkanes. What is haloalkanes? Haloalkanes. By the definition we know that is there is a halo group present, that is halogen group present in the alkanes. So when one hydrogen is replaced, or when hydrogen is replaced, in simple, when hydrogen, not just one, there could be many, when hydrogen is replaced by halo group, it is called haloalkane. In alkyl groups, not in every group, in alkyl groups, that is carbon is sp3 hybridized. In this, if the halogen is replacing hydrogen, then it is called haloalkanes. Example, C2H5X. This is monohaloalkane. And there could be one more, CH2X. This is dihaloalkane. Then when you have three of those, this trihaloalkanes. Okay, this is the three things. These are the examples of haloalkanes. Now when you have only one substituted, then it is mono, two, then it is di, and then when it is three, it is tri. Now going to haloarenes. What are haloarenes? Haloarenes. Similarly, when hydrogen is replaced by a halo group, that is X, in aromatic ring. This difference is aromatic ring. Then it is haloarenes. Okay, simple. So now examples could be, one very best example which I could fetch is, this is monohaloarene or monohaloarene. Yeah, monohaloarene, and they're also called aryl halides. And monohaloalkanes or haloalkanes, as in simple, are called alkyl halides. So next time when we are using terms like aryl halides and alkyl halides, you should not get confused. So I'm just specifying it at the very beginning. Monohalo. So here we have one example, that is mono. This is nothing but monohaloarene. One more we have is when two are substituted. When you have one benzene ring and you have two substituted, then it is dihaloarene. And when you have three substituted, then it is trihaloarene. This is how it is, done. Next, and this is also classification of, there are three types of haloalkanes and haloarenes based on the number of X. This is three: mono, di, and tri. Mono, di, and tri in both. Now we'll go to one more very important basis of classification. Classification on the basis of compounds having sp3 compounds having sp3 hybridized carbon X bond. Okay, so in this you have three. It is classified into three things. That is, first is alkyl halides. What are alkyl halides? Which we studied. That is nothing but haloalkanes. When X, that is halogen, replaces a hydrogen from alkane, it is called alkyl halides. Example can be C2H5Cl. Okay, ethyl chloride. Okay, ethyl chloride. Next, we have second type of this thing, and in this alkyl halides, again, this is divided into three types. When you have one R group, that is one alkyl group, when there's one R, okay, when there is one alkyl group, it is primary alkyl halide. When there are two, like R, let's take CH2R, and then R, and then Cl. Then this is CH. Then this is secondary alkyl halide. Now when we have three, this R. This is tertiary alkyl halide. Okay, so in the alkyl halides, again there is three divisions, that is primary alkyl halide, secondary alkyl halide, tertiary alkyl halide, based on the number of alkyl groups. This is based on number of alkyl groups. Okay, next we have benzylic halides. So no, next we have allylic halides. Second we have allylic compounds. What are allylic compounds or allylic halides? So these are when halogen is next to a carbon double bond. Okay, halogen is next to carbon, which is beside carbon double bond, is attached to carbon, that is next to carbon double bond. One example I could give you is this, and these two are examples of allylic compounds. Next you have benzylic compound, benzylic halides. Whenever this benzylic halides, people get attached with whether the halide is part of benzyl ring or something, a benzene ring, but no, here halogen is attached to carbon, which is attached to benzene or aromatic ring. Okay, best example that I could give you for this is this is benzyl halide. Next, how will you classify? Next is classification based on carbon halogen bond, where carbon is sp2 hybridized. Okay, so in this you have two. First is phenylic halides. So in this, the carbon halogen, that is the halogen atom, is bonded to sp2 hybridized carbon. Okay, so example is this, that is X is bonded to carbon which has double bond. Okay, this is one of the example, and one can be these two are vinylic halides. Then you have aryl halides, which we already learnt. Aryl halides, where halogen atom is bond to carbon atom of aromatic ring. Okay, so you have this. This is the classification. Now we're going to the most important part of the organic chemistry, that is nomenclature. Nomenclature. So first we'll go nomenclature of haloalkanes, which is first is choose the longest chain, which is constant for all of them. Choose the longest chain. Choose the longest chain. So why is choosing longest chain important? Is because it is the very much basic rule of the nomenclature. That is, you always choose the chain which has more carbons, more number of carbons. You choose the longest chain, which has been a part of nomenclature for when we studied general organic chemistry, and in 10th when we studied carbon and compounds. This is what goes for the haloalkanes as well. Next, halogen. Halogen is attached to no, halogen is attached to the carbon that is given least number. Okay, so the halogen should get least number. Next is if there is double bond or triple bond present, it should be given bond present. It should be given more preference. More preference or first priority. And then using prefix when there are more than one halogen. It is advised to use more number of it's advised to use prefixes like how we used in the first try ditetra. So you have to use these prefixes when there are more number of halogen. And name it on the base of bond. If there is bond presence, name the bond as well. Like haloalkane or haloalkene or haloarene. Sorry, haloalkyne. So you're supposed to name if there is any bond present. One example we will take to understand this nomenclature. Just one example. So here you have 1, 2, 3 carbons, or 1, 2, 3. However, you name the chain, the longest chain is of 3 carbon, which is, this is the longest chain, and this chlorine is attached to the second carbon. So you can write this as 2 chloro, and what are the number of carbons? Total propane. So it is 2 chloropropane. So this is how you will name the haloalkane. Now going to haloarenes. First rule of haloarenes is, these are also called aryl halides, which I've already mentioned. Just in case we use these terms for the next, you should not get confused. So they are also called aryl halide. You should give number preferences, number prefix if more functional groups are attached, or else it's okay. And also specify the positions that halogens occupy. So in haloarenes and in aromatic ring, you have 3 positions, that is para, ortho and meta. So you have to specify the positions that your halogen has taken. And halogen here also gets the least number. Halogen gets more priority, or in simple words, least number. So one example we have here is this. So we are going to name this carbon 1, 2, 3. So we already know there's 6 carbons, and we can count these things as well. But here we are going to give 1 to this. So we're going to go this way for the counting. So this gets 1. So it is 1 bromo. So you don't have to write 1 bromobenzene. You can just write bromobenzene. But to be specific, you can mention para bromobenzene. As simple as that. Now, since we learned the nomenclature, classification, now we will move on to nature of the carbon bond. That is nature of C and X. X is more electronegative in nature, right? Hence, when C and X form a bond, this gets partially negative and this gets partially positive charge. Okay, so they are having polar bond. Polar in nature. The bond is polar in nature. Why is it important to understand this? Is because most of the chemical properties of a bond, of a haloalkanes or haloarenes, are dependent on the nature of the bond. Next is bond length. Bond length here increases as we move from CF to CI. And why does this increase? Due to increase in size of halogen atom. Halogen. As you know, F is smaller than chlorine, smaller than bromine, and smaller than iodine. Hence, this increase happens. So, CF, CI, now CCl, then CCl, then CBr, and then CI. This is the nature of the bond length. This is how bond length will increase, and this is due to increase in that. Now we will see one most important topic, which is very common in all organic chemistry, which is like a part by part we are going. That is preparations. How are haloalkanes and haloarenes prepared? So first, how is haloalkane prepared from an alkane? Preparation. First is from alkane. When you're taking, we'll take one alkane, that is ethane. This method is direct halogenation using the UV light or using the light. Plus chlorine. In the presence of UV light, you will get C2H5Cl plus HCl. Now this is there is no, you don't have to study mechanism in the chapter, but we will just say in simple, this is a free radical reaction. It is a free radical reaction. Okay, so there is formation of radicals like this, and then they will attack on ethane, and it will form ethyl chloride. Okay, from alkane, this is how you prepare this haloalkane. Now from alkene, we will prepare from alkene. So here we will take one symmetrical alkene first, plus acid or HCl containing halogen. You will get X. But now, when you take unsymmetrical alkene, let's take this type of, this is prop 1 ene. Okay, this is what is this? Prop 1 ene. So when you are adding acid to prop 1 ene, where will the Cl and H2 go? Because they can go to this carbon or this carbon. Which carbon will they go? So here you follow Markovnikov's addition rule. You follow Markovnikov's What is Markovnikov's addition? This is something which we have studied in RGOC also. Markovnikov rule, which is negative addendum. What is negative addendum? Negative addendum is the part of, it is the negative or nucleophile in simple. Negative addendum is nothing but nucleophile. Negative addendum, which is negative in nature. Negative addendum always goes to carbon that has few H. Okay, so by Markovnikov's addition, like Markovnikov's rules, which I explained you now, the negative addendum always goes to the hydrogen that has less number of, always goes to carbon that has less number of hydrogen. In this carbon here has three hydrogen. This also has 3 hydrogen, this has 2 hydrogen, and this has no hydrogen. So when you add this, it will become this CH3, and then you have CH, and then you have CH3, and then Cl. So this is going to be this is H, sorry. Yeah, so this is going to be here one group, this is a chain. So this one has only one H, and this has 2H, and this has 3H. So this will be CH3, C, and H, and CH2, a single bond. So now negative addendum goes to the carbon with few H. So bond is broken between these two. The cleavage has happened between these two, or the bond is broken between these two. So negative addendum goes to the one which has few electron, and this H goes here. So it will be CH3, CHCl, CH3. This is what is going to be product at the end. This is how you will prepare through Markovnikov's addition rule from alkene using acid. Next, from alcohols. This is a very common method of preparation because alcohol, this preparation has a lot of possibilities. First one is alcohol plus HCl in the presence of anhydrous zinc chloride, which is going to give you RCl plus H2O. This together, this HCl and anhydrous presence of this is called Lucas reagent. Lucas reagent. This is one method of preparation. Then you can prepare it through phosphorus halides, using phosphorus halides. How will you prepare through phosphorus halides? Is you have 3ROH plus P. So you will get 3RX plus hydrogen acid. You will get one acid and this compound, number of 3. And then thionyl chloride, using thionyl. This is only for the preparation of or the substitution of chlorine. Not all halides can be prepared through this method. Only for chlorine this is very useful. You have alcohol plus this is thionyl chloride, giving you plus sodium dioxide gas and HCl. These are the preparation methods of haloalkanes. Now we will see the preparation methods of haloarenes. How haloarenes are prepared. So first preparation method is nuclear halogenation. Nuclear Now what is this nuclear halogenation? You take a benzene plus Cl2 in the presence of Fe. So you heat and then you get this is nuclear halogenation. One more method is from phenol. You have phenol group plus PCl5. This method can also be used in haloalkane, that is PCl5 plus ROH, which is also going to yield you a haloalkane. You get C6H5Cl plus HCl plus POCl3. This is what is going to be the reaction. Next, one more very common way of preparation of haloarenes is Sandmeyer's reaction. So, Sandmeyer reaction is treating diazonium, azonium, azonium salt with copper chloride or copper bromide. You treat it with copper chloride or copper bromide, which is we will do. What is a diazonium salt? We will see what is a diazonium salt first. This structure is diazonium salt. So when you treat it with CuCl in the presence of HCl, you will get this structure Cl plus N2. Now if you use this in presence of CuBr and HCl, you will receive this plus Cl. And one more reaction which can be done is with Ki and heat or warm. You will get plus N2 plus Cl minus. This is the methods of preparation of haloarenes using nuclear halogization from phenol and Sandmeyer's reaction. Now going to physical properties of alkyl halides. Okay, physical properties of alkyl halides. Physical properties of both alkyl halides alkyl and aryl halides. Okay, so first you have alkyl halides. So alkyl halides, color, first physical appearance, color, usually colorless. Usually you don't have much color or it is colorless in pure form. Then you have smell. As we know, we have already tried of how the smells of alkyl halides are. They're usually volatile and they smell sweet. Sweet smell. Boiling point. Boiling point is high than their parent carbon. Then parent, what is higher than parent hydrocarbon? Parent hydrocarbon is the alkane group, alkyl group or aryl group that is present with them. So it is more than them. Then parent and hydrocarbon. Carbon. And order of boiling point is R has more because the bond length is more and also the ion halogen size is more. Then R, Br and then R. Cl and then R. This is because halogen size so van der Waals force is also more. Okay. Now going to aryl halides. Aryl halides. What are the physical properties of aryl halides? In this, main point is para isomers of these or para groups, para substituted subs are more stable, or you can say have high boiling point or high melting point. Why do they have high boiling point or why high melting point? Is because due to symmetric reasons. So density increases with more number of X and C. Okay, so more number of for alkyls with R it increases. With R it increases. Next, haloalkanes are poorly soluble. They are poorly soluble due to and aryl halides also. And aryl halides also. Why are they poorly soluble? They're poorly soluble due to absence of H bond, that is hydrogen bond. Due to absence of hydrogen bond, they don't have much solubility with the water, because water cannot form hydrogen bond with the subsequent compound or alkane and haloalkane, and it hence cannot have that great solubility compared to the parent hydrocarbon. Going to now chemical reactions shown. First is substitution reaction. Substitution reaction. So substitution reaction, that is here which shown by alkyl halides of alkyl halides. Which are the substitution reactions shown by alkyl? They show nucleophilic substitution. Nucleophilic substitution. Okay, so it may take place in two mechanisms. SN1 mechanism or SN2 mechanism. It may take place in two mechanisms. Now we will study about SN1 mechanism, that is the reactivity for how SN mechanism works. So first, SN1 mechanism. So how does SN1 mechanism happen, or how does SN1 mechanism take place? Is there is three steps involved in the SN mechanism. So SN1 mechanism contains three steps. That is, first is you have a alkyl group. Let's take RX. The X leaves first. That is, X is leaving. This is the first step, and this is a slow step. Slow. So this is rate determining step. Okay. Next you get a carbocation. Carbocation. Okay. You get a carbo. After the formation of carbocation, the attack of nucleophile attack takes place. And then you have, this is fast. Then you have R nucleophile. This is the SN1 mechanism in simple. Now we'll take one example to understand it much better. So example is, I'm taking a tertiary haloalkane, that is H3 CH3 CH3 to Cl. So first step is Cl will leave. Okay, so you will have CH3 CH. No, you will have C, and this is positive carbocation formation. This is rate determining step. After this, you have nucleophilic attack. So let's take addendum to be H2O plus H2O. Let the nucleophile be water. Okay. So now H2O. So how will H2O attack is, and water has this. It is negatively charged, so it will attack either from here or from here. Okay. So when it attacks, it will form this structure. Either this structure, if it's from back, then it will form this structure. Then it will form this structure, which is inverted, and from front it will form this structure, which is C and O, H and H. Now just because we added water, it doesn't mean that we have only one molecule of water. So there will be many molecules of water. So one more molecule of water which is very nearby it will take the H. We see. So now we have one more water molecule approaching, which is this. So this will attract one H. So now this will be C, then O, H, H, and O, H, H. So H3 will leave. Plus H3 minus H3, sorry. So minus H3 plus. So you will be left with either this compound or this compound. Here this is retention, and inversion. There will be two products you will get, retention and inversion. Both of these will be 50% and 50%. They are racemic mixture. So what is racemic mixture? Formation of two compounds. That is, one is inverted compounds and one is retained compound. And these two are 50-50%, and these two together are called racemic mixture. And this process is racemization. Okay, this process is racemization. So in SN1 reaction, one thing you have to keep in mind is products are give racemic mixture. Racemic mixture and carbocation is formed. So now we will see the conditions required for the same. The first condition, okay, first conditions, or we'll see first reactivity order of it. Reactivity order. What is a reactivity order? Why should we see which alkyl halide reacts how to the SN1 mechanism? It is because to understand that why tertiary alkyl halides are more reactive. So reactivity order. There is carbocation formed, right? So this carbocation has to be it is formed. So this carbon cation should has a lot of positive charge. So if there are alkyl groups present, let's take they stabilize the carbocation and it is more stable. So more the alkyl groups, more the stable the carbocation will be. So more the R group, more stable, will be carbocation. Okay. So this is the reason why we need reactivity order. So the reactivity order goes like benzyl. Since benzyl is because it has benzene ring, so resonance also is there. Then allyl, then tertiary, secondary and primary. This is the order of reactivity. Okay, this is very important in the perspective of boards. This is very important with the perspective of boards because you're usually given the questions in MCQs that which one of these is more prone or more reactive for SN1 mechanism. Now conditions which we need for SN1. Conditions for SN1 reaction. What are the conditions we require? First is carbocation should be stabilized. So polar solvents be it protic or aprotic are required, okay, because they during solvation they add electron density. Hence you use polar solvents, be it protic or aprotic. And you need weak nucleophile for this. nucleophile. Okay. Now we will go to SN2 mechanism. SN2 mechanism is very fast. There is no, there's no formation of carbocation or such product. There's only one intermediate which is formed, and then reaction takes place very fast. So SN2, we will give a clear mechanism first. R. Let's take CH. CH of. We will take very primary alcohol, that is primary H. C. Okay. Now this is what we have taken, and we will take negative addendum again, H2O. Okay. So nucleophile is OH minus. Okay, OH minus is the nucleophile. Now first, see this leaving group leaves, and nucleophile is attacking. So you get steps like this. You will get an intermediate first, that is C and OH, H, 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 and leaving group is not yet left. So you have Cl also. So attack and leaving takes place simultaneous. Hence you have one intermediate formed in between, and then next step follows by leaving group leaving the group and nucleophile attacking it. So next step is CHO. This is how the things happen, and here you form inverted product. Why always SN2 gives up with inverted product is main reason. The most important reason is because the backward attack of nucleophile. So backward attack of nucleophile always results in the formation of inverted product. This is called Walden inversion. It's called Walden inversion. Next, now reactivity order, we'll see. Reactivity order. What is reactivity order for this? So for the reactivity order, you have primary all alkyl group reacts more, and then secondary alkyl group. Primary alkyl group more than secondary, and then tertiary. Why is this opposite to SN1 mechanism? Is because steric hindrance slows down. Steric hindrance slows down. So see, when you're attacking, if I have bulky groups, the nucleophile cannot attack backward. So you cannot have more bulky groups here, right? If I keep R group, and R group, that is alkyl groups all around, it becomes bulky. When the area is too crowded, like this, just imagine the area is too crowded. How will you enter? How will you enter in the crowd? But when the lines are like this, when the road is like this, you can clearly see you will enter in the straight way. This is how it is going. And the road is like this, it is tough for you to enter or come in. When the roads are clear with people just scattered rightly, it's easy for you to travel. And this is how SN2 mechanism also goes. If you keep bulkier groups, how will the nucleophile attack? The leaving group will leave, but Nucleophile attacking becomes a tough job, because it is a very fast process, and it does not form carbocation in the middle, and it does not have that, it will wait and all. It has to be fast. So for that, the attack has to be fast, and for that attack, the groups should be light. Hence, steric hindrance slows down the reaction. So this slows down reaction. Hence, this is the reactivity order. Okay. So now, what are the conditions for this to occur? Conditions. Conditions for SN2 mechanism to occur. For SN2 for SN2 to occur. What are the conditions? So there we saw few conditions for the occurrence of SN1 mechanism. What were the condition of for this is carbocation should be stabilized. So polar solvents we use, and this is that the polar solvents are used during solvation of the polar, the alkyl halides. They release electrodensity, which in turn stabilizes the carbocation. So carbocation stabilization is more important. To achieve that, we are taking few steps that could be polar. This whole SN1 mechanism can be taking place in polar solvents to increase the during solvation electron density, which in turn stabilizes the carbocation. So for SN2 mechanism, what are the conditions similarly? So for that, you usually prefer 1-degree alkyl groups. Other one is you should use aprotic solvent. Aprotic solvent. They Why should you use aprotic? What is the point of using aprotic? There should be some reason, because all of these things are happening due to some reasons. No scientist is just using some solvent for creating a mechanism, because they need certain things. So for everything you need a reason. You need something to achieve. So here what we have to achieve is we have to provide less steric hindrance. In that, our achievement here to use is carbocation should be stabilized. Whatever we use, whatever we do in that reaction, our main goal is to stabilize the carbocation. Here, our main goal is to give less steric hindrance. So for that, we use aprotic solvent, because it gives less steric. It gives less steric hindrance. It gives less steric hindrance. So they use aprotic solvent. And next is we should have good leaving groups. So obviously here you have a good leaving group, that is X. So X is already a good leaving group. Okay. So that is about the things. Next is nucleophilic substitution in haloarenes. Nucleophilic substitution in aryl halides. In aryl halide, there is no nucleophilic substitution. Okay. In aryl halides, no SN reactions. No SN reaction. Why there is no SN reactions in this aryl halides is because of the partial double bond. Let's take this aryl halide as an example first. We will see how an aryl halide looks, right? We have an idea. We all know, since we studied now same thing since long time, like since now we have studied the preparation of how aryl halides are formed. We will see this look of how it is there. This is an aryl halide. So this directly attached gives it a partial double bond character. Partial double bond character. Because of the resonance, it is partial double. Resonance, there is a partial double bond. So it is tough for leaving group. So it is tough for leaving group. Tough for group. Tough for leaving group. So it is tough for the leaving group to leave. Because see, here we are already discussing that there's a double bond formation. So it is tough to break the double bond, right? Leaving group. That is what we've been knowing. We know this since the GOC when we studied. We know that it is tough to break the double bond. So there's a partial double bond character. Hence there is resonance. Due to resonance, so it is tough for leaving group to leave. Hence no SN reactions. Okay. This is the reason they don't undergo SN reaction. But they have electrophilic substitution. They have electrophilic substitution. What is an electrophilic substitution? First of all, what is an electrophile? What is an electrophile? Electrophile is positive addendum. Right? We know what is a electrophile. It is a positive addendum. So, positive addendum. What is the role of positive addendum? How electrophilic substitution happens? First, we have halogenation in this. Where you have plus Br, which will give you so the positive addendum in Br2, that is Br2, radical, it gets substituted into this and it forms, sorry, this is Cl, this is Br, and this is a formation of this one. Next you have nitration. A nitration reaction, that is the reaction it shows, nitration. Nitration reaction. What happens in nitration reaction is you have a chlorobenzene. Okay, this is a chlorobenzene plus HNO3, that is nitric acid. You use nitric acid, that is presence of and H2 SO4 and heat, you will form NO2. So nitration is an example of aryl halides. It is an example of nucleophilic addition. So we have this H2SO4 and heat. So next you have electrophilic addition.